active and exciting field of research. So we decided to organize this school for PhD students and young postdocs to become familiar with this activity and find opportunities for future research. We are gonna have 70 lectures in 4 days, so about 4 lectures per day. We encourage everyone to participate actively, and especially students and postdocs, please ask questions, interrupt at any point you have questions, ask questions. So we want this virtual meeting to be as active as possible. So we start today's session by Irene Valenzuela from CERN and University of Madrid. And she will deliver 4 lectures on introduction to the Swampland. We try to record these lectures, if it's okay with you, Irene, and we'll put it on YouTube. So thanks again, Irene, and please take it away.
Okay, thank you very much. Thank you for organizing this. I think it's a very nice initiative, and thank you to the students for coming and be willing to learn about this new exciting topic, which is the Swampland program. So before I start, let me also say my voice is a bit terrible today because I was a bit sick, even if it's not COVID. But if you cannot hear or understand something I'm saying, please just interrupt, okay? I will not feel bad about it. Just interrupt at any moment. Like, what? Sorry, what did you say? I couldn't understand. And who will blame me to my voice and not only to my pronunciation? Okay, so the plan is to give some introduction to the Swampland program. Then you will hear more advanced topics by the other speakers. But then it's very important that you ask any question that is in your mind, because this is the moment in which I will not assume anything about the Swampland, and you can ask, okay? So don't feel afraid about it. Okay, so I put here some references, okay? I can also send the slides later on if you wish, no, as you prefer. But basically, I mean, there have been different reviews on the Swampland. I am remarking, I'm remarking this one because I wrote it. So I will follow closely these lectures that you can find in archive. But you can also find much more information, for example, in this one, which is much longer, okay? Okay, very good. So what's the Swampland program? I mean, probably you have already heard a few things about it last week, sorry. But let's start really from the beginning, okay? So we are very used to work with effective field theories in physics, right? Like we are used to have some effective field theory that describes the physics up to some energy scale. And this has been a success, like it has been very useful to complete the standard model of particle physics or cosmology. But as we are going to see, some of the expectations that come from effective field theories can break down, can be wrong once we include quantum gravity. Okay, so as I said, like we used to have, I mean, what's the point? So if we have some theory in the UV, we know that we can always integrate out some high degrees of freedom up to some cutoff and obtain an IR effective theory, right? So we will write, for example, some Lagrangian theory, which is weakly coupled to gravity, such that we have some renormalizable part plus an infinite sum of non-renormalizable operators. Okay, so far so good. And this is valid up to some energy cutoff. Now, the question that we are trying to answer here is whether the reverse can always be done. Okay, so whether given some effective field theory that you construct following the rules of quantum field theory, whether this can always be UV completed at higher energies in a consistent theory of quantum gravity. Okay, so this is a theory with gravity. And the point is that the answer to this question is that no, not everything can be done. Okay, so there are some rules, there are some constraints, and this is what we are interested in. Okay, so not every EFT can be UV completed in a quantum gravity theory, like string theory. Okay, so this is something that we have learned from string theory, and we know that it's even true in quantum field theory that not everything can be UV completed, but with gravity it's even stronger. I mean, the constraints can be much stronger, and the goal is to understand what these constraints are. Okay, so determine the constraints that an EFT must satisfy to allow for a UV completion. And this is where the tricky part is. I mean, it's easy to say that there are some constraints, but the difficult part is to find in a precise way what these constraints are. Okay, any question at the moment? Okay, good, very easy. So this is the typical picture. So the point is that if you imagine all possible EFTs you could construct at a given energy scale, not all of them will be UV completed, and those that can be UV completed, we say that belong to the landscape, while those that cannot, okay, so this is not consistent with quantum gravity, those belong to the swampland, while the landscape is consistent. And the thing is that these constraints typically become stronger and stronger as you increase the energy. Okay, so sometimes the constraint is not just some, I don't know, some feature that is independent of the energy. I mean, sometimes the constraint is also correlation with the cutoff. So such that if you have some effective theory which is valid up to this energy scale, if you continue increasing the energy, at some point it's going to stop being valid unless you introduce new physics or some new degrees of freedom or something else. Okay, so it's typically these are constraints that depend on the energy scale at which you want to use this EFT. And this is important also because all these swampland constraints, okay, that you need to satisfy to belong to the landscape are going to disappear if gravity is not dynamical anymore. So if the Planck mass is sent to infinity. Okay, so of course, if you send the Planck mass to infinity, then everything, this cone becomes very large and everything is allowed. So we only say that a constraint to be UV completed is a swampland constraint if it's really tied to gravity, so that if it disappears when the Planck mass goes to infinity. Okay, and as I said, one of the basic things we will learn is that the cutoff of the EFT can be lower than the Planck mass. Okay, so at some point you will need to introduce new things such that the EFT continues being valid. Okay, good. So why is this interesting? Well, of course, it's interesting by itself to understand the constraints that quantum gravity imposes, like what is the difference between having gravity or not. But also, if we can give these constraints for EFTs, I mean, this is like the quantum gravity imprint at low energies. So they can have phenomenological implications. And this is the long-term goal. Okay, so the goal is to be able to give to someone working in particle physics or in cosmology some clear recipe of what are the rules that they have to apply such that the EFT that they construct will guarantee to have a UV completion. Okay, so they can be like new guiding tools to construct new models beyond the standard models. And also we have proposals that they can be used to solve the naturalness issues that we observe in the universe. Okay, because now there are new constraints. So all the logic of naturalness and fine-tunings and all these things have to be revisited in terms of gravity, because maybe what you think is not natural is natural from a quantum gravity perspective. Okay. Good. So how come these constraints can be so powerful? I mean, because I'm not saying just that the full tower of non-renormalizable operators will, of course, will be sensitive to the UV and you can put bounds there. What I'm saying is that even the renormalizable part, like the effects are not irrelevant in the IR. Like these constraints can be much stronger than what one expects. And how is that possible? Because this breaks with all what we have learned from quantum field theory, that we expect some decoupling of scales. Like the effect of the UV kind of disappears when you go to the IR. So how is this possible? Well, what happens is that quantum gravity is different than quantum field theory. Okay, gravity is different in the sense that can induce some UV-IR mixing. So, for example, if you think of black holes make manifest some correlation between higher energies and long distances. Okay, so high energies and small energies. So imagine that you have, like, I don't know, two particles scattering. Typically, if we want to probe the physics at smaller and smaller distances, we have to put more energy into the system, right? So high energy is equivalent to a small distance. But at some point, if we continue adding energy to the system, what we are going to produce is some black hole. And the black hole is a large object, and the more energy we put, the larger it is. So putting more energy in the end translates again to large distances. Okay, so this notion of UV, IR, large distances, small distances is very well defined in quantum field theory, but in gravity gets mixed. And that's why we think that all these constraints coming from quantum gravity can be stronger than what we think in the IR and can be really used for our universe. And in particular, sometimes they go against the EFT expectations. So the examples that we will see that are like the main examples. Oops, sorry. What happened? Sorry, 1 second. It's connecting again. So let me see. So the examples that we will see that are more important for the Swampland is the absence of global symmetries and the fact that small gauge couplings and large field ranges are problematic in quantum gravity. Okay, so let me share again. Okay. So global symmetries, small gauge couplings, and large field distances are things that are completely fine in quantum field theory. Okay, there is nothing wrong with having a global symmetry or having a small gauge coupling. We even like it. We have control. But these things we are going to learn that are actually problematic in quantum gravity. And this has non-trivial implications. Okay, any question? This was kind of an introduction. Okay. So after this introduction, the plan of the lectures for this week is that I will start reviewing the basic notion of why there are no global symmetries in quantum gravity, which is the oldest and basic Swampland principle. And then we will understand why these small gauge couplings and large field distances are problematic. And this comes from introducing what are called the weak gravity conjecture and the distance conjecture. So during the rest of the week, except for today, we will be talking about weak gravity and distance, okay? Because they really play a central role in the Swampland program. And we will see how these conjectures are motivated from the point of view of string theory, what is the evidence that we have, and also how we can motivate them and find evidence by thinking of black hole physics. And then I think in the other lectures, you will hear more about recent developments regarding no global symmetries. Okay, I will just focus on the basic things, but there are many more things that can be done. And then in the others, you will hear about constraints on the scalar potential. Okay, that I will not deal with in these lectures. So Thomas Van Riet, Lars, they will talk more about the landscape and the scalar potentials. Okay. So if there are no questions, then I will start with the first basic Swampland principle. Can you hear me well? I mean, even with my voice and everything?
Yeah, everything's okay.
Okay, good. Just checking.
We don't feel good that you feel ill, and but it's okay.
It's fine. So since I think people are a bit shy, I'm gonna do one thing. So those of you who are listening,
I ask again to ask questions. Everybody, please be active.
Yeah, so those of you that are listening right now, I'm gonna ask you a question. I mean, I just want to know who have already heard about the absence of global symmetries and that this is some swampland constraint that we must impose. Okay, so you can take and you can raise hand or I don't know, like have some reaction on the chat. Okay, very good. It seems okay. Some people have heard about it, not everyone. That's good. You will learn about it. Very good. Okay, so let's continue. Okay, so no global symmetries. So the statement is that any global symmetry in quantum gravity must be broken or gauged. So there are no exact global symmetries that are not associated to some gauge degree of freedom. Now, this is what I put here, okay? Any global symmetry must be broken or gauged. Now, in order to understand this, it's very important to understand what is the definition of a global symmetry, okay? What is the difference between being global or gauged? Because it doesn't mean that there are no symmetries in quantum gravity. It just means that they are associated to a gauge field in the sense that we can measure this symmetry from far away. Okay, so let me give you some intuition. Okay, the intuition between the difference between global and gauged, okay, is that global symmetries are associated to conserved charges that cannot be measured from far away. While a gauge symmetry can be. Okay, so what does it mean this? Like think of, for example, let me take an example. Think of the standard model of particle physics, okay? And think that you have all the possible scattering processes that you have within the standard model. Now, there are different types of symmetries in the standard model. Some of them are global, and some of them are gauged. So to give you an example, the electric charge, right, is a conserved charge. Like all the processes must respect electric charge. And this is a symmetry which is gauged. Okay, because it's associated to some gauge field. And it's like the global part of the gauge group. Okay, I'm not talking about global local transformations, but like the global part. So it's something that acts on the Hilbert space, the physical states of your theory. And you can measure, I can measure what is the electric charge in a given region of space, because I just have a Gauss law and I can integrate in, and I know that the conserved charge, that the charge is conserved. And I can design an experiment to measure how was the electric charge inside of a box. Okay, even if I am very far away from the box. However, another type of symmetry, for example, B minus L, so the baryon minus lepton number. This is something which is also happens to be conserved in the standard model, but it's global. Okay, so this is global symmetry because there is no way to know how many baryons and leptons you have if you are infinitely far away, unless you just go very close and count like how many have. There is no gauge field that can bring this information far away. There is no Gauss law associated to it. So this is kind of the intuition of what are the symmetries that are allowed and which ones are not allowed in quantum gravity. And it's kind of a holographic picture of the universe that in the end, like it's only those things that you can measure like from a possible boundary, like very far away, that really makes sense. And if you cannot describe it from far away, there is no way to make sense of it in quantum gravity. Okay, this is kind of the intuition. So of course, this is just like a physics intuition. I think I coordinated with Miguel later on, so that he's gonna give you like some formal definition of global symmetries in terms of the topological operators, because recently it's very useful to use all these formalisms, and then using that formalisms, you can also see that the difference between being global and gauged is that the charged states, the charged particles are gauge invariant or not, and you can describe it in terms of topological operators. But at the moment, just try to keep this in mind, okay? If it's something that you can measure far away, is gauged, otherwise it's global and should not be allowed in quantum gravity. Any other question?
That includes the confined phase and the Higgs phase, or we will talk about it later? If a gauge symmetry is confined, or is
good. So if it's confined, I mean, the gauge group is confined, like you don't have asymptotic states. The point is that there is no, I mean, like the global part of the gauge group, it's still something that you can, that is conserved, right, in all your processes, like the color charge. And that's it. I mean, in the end, it's trivial because that's going to be trivial because you don't have asymptotic states with a given charge. So in a sense, you can also measure it, but you're always going to get the same result because you don't have asymptotic states carrying different values of the charge. But yeah, like, I mean, you can measure it and it's zero. So that's fine. That's part of being gauged. So there is, in this difference, it really doesn't really matter if it's Higgs or confined or anything like that. Okay, as long as somehow, I mean, it's going to be associated to some gauge degree of freedom, like the global part of the group, I mean, will be gauged and it will be fine. Okay.
there is one more question.
Good question.
Hi, excuse me. I just, can you hear me?
Yes.
Yeah, thank you. Okay, so if you think about the gauge coupling as a continuum, does this no global symmetry assumption provide a bound on how small the gauge coupling can be? I mean,
very good. So not now. At the moment, this is just about, I mean, as long as it's gauge, it's fine. Doesn't matter what the value of the gauge coupling is. But we will see tomorrow that, of course, that's not very useful. I mean, because if it can be super tiny, I cannot detect it, so who cares? But we'll see tomorrow that there is a way to make this stronger. And that's precisely talking about the weak gravity conjecture. Okay, so just saying that there are no global symmetries is not enough to be constraining enough. But tomorrow we'll see how to make all these statements more constraining precisely by quantifying how much you have to break the symmetries and how tiny the gauge couplings can be. Okay?
Yes, thank you.
Okay, good. So let me give you another example, just so that everything is more clear. Yes, please. Go ahead.
Hi, I just wanted to ask one question. You say that we don't have global symmetry in quantum gravity. Am I understand right that it means that quantum gravity must be universal and be everywhere? So this is the reason that we don't have global something like that.
If it's universal, you mean like if there is only a quantum gravity theory? That's what you're asking?
Yes, yes.
Yeah, so we don't know. I mean, so the point here, the goal is try to find out what are the universal constraints that a consistent quantum gravity description imposes regardless of whether there is more than one. Right? Like, for example, with quantum field theory, you know that, I mean, we can have many different quantum field theories, but still we know that all of them have to be anomaly free, right? Like, we cannot have anomalies. So the question is, what are the rules now? I mean, being anomaly free for gravity is not enough. There are more constraints to have a unitary quantum gravity completion, and I mean, we try to understand which ones. Now, it's a very interesting question to see if in the end there will be only one quantum gravity theory, so that everything is connected somehow or not. And this is also something that we try to understand in the Swampland. Like, we'll see that, I mean, I think Miguel will explain that assuming, like, for example, if we think that no global symmetry is a general thing, you can try to understand whether everything that would be consistent with quantum gravity can arise from string theory or not, and try to answer the question of whether string theory is unique, which is very interesting challenge. But this is like a second order question. Okay, so right now we just try to understand what are the general constraints. And of course you can say, okay, how you do that if you don't know all possible quantum gravity theories? So the thing is that we will use black hole information, we will use string theory, we will use all the tools that are at our disposal to try to identify what these constraints are. And I will give you the evidence for the absence of global symmetry in a minute. Okay. Good. So let me give you another example, and then we will go to the evidence to understand why we think this is true. Okay, so another example is just consider some scalar field, okay, some free scalar field, like some action. It's invariant under a shift transformation, right? And this is a global symmetry. Like, there is no way to design an experiment to measure this, and there is no gauge field associated to it, anything like that. It has a global charge, which is the integration of the current, because this is just a continuous symmetry, which is just phi. You can just complete it by using Nether theorem, right? By Nethers. And it's a conserved symmetry, right? Because by the equation of motion of the scalar field, you can already see that the current is conserved. It's a conserved current. Okay. Okay, this is just plugging this here. Okay, so what happened with it? Well, this global symmetry, this is a global symmetry, so this will not be allowed in quantum gravity. So we cannot have just free scalars. Now, what can we do? What happens? What is string theory doing in these cases? Well, there are two options. We can break it by adding a potential, some scalar potential, so the symmetry is not a symmetry anymore, or we can gauge it. And as you have probably learned many times, we can gauge it by coupling this scalar, this action, to a gauge field A, such that my new theory is given by my scalar field plus the coupling of this gauge field to the current, and it must be a dynamical gauge field. So I have also the kinetic term, and this is the usual Stuckelberg coupling. Okay, such that the theory now is only invariant under the combined transformation of the scalar field and the gauge field, right? And now here I have different types of like symmetries or redundancies, right? Like we have the case in which lambda, like this parameter, at infinity goes to 0, and this is just some local gauge transformation, which is just a redundancy. Okay, this doesn't mean that has no physical meaning actually. It's a redundancy. But then we also have what some people call the global part of the gauge group, which are those transformations that do not vanish at infinity. And this is what I'm calling that is a global symmetry which is gauged. Okay, so it's gauged global symmetry. So the language is very confusing because like we use this same word for different things. So that I'm trying to do this example to make clear what I mean when I say that a global symmetry is gauged and therefore is consistent in quantum gravity. Okay, so this is the case which is good. We are happy with this one. Okay, and has a physical meaning, doesn't vanish at infinity, acts on the Hilbert space, but it's gauged. Okay, because it's in combination with this gauge field, and the charge operators are not gauge invariant, so you cannot just have them alone. And this symmetry is what we call the electric charge, is the usual electric charge. This conserved in nature. Okay, so this is the current, which is just the electric charge. Okay, so this is the easiest example we can think of. Is there any question?
Yes, there is a case that we can have a scalar interacting with the others by derivatives. It is just derivatively coupled, but it has interaction. It's not trivial, so it means that it's not consistent with quantum gravity. It is not gauged, right?
Well, if it's just interacting with derivatives, then the symmetry is preserved, right? Like it's not broken, which means that that's not possible. It cannot just be that. Either it's gauged, or if it's not gauged, then you have to add some scalar potential. You need to add something that depends not only on the derivatives. Oh, sorry, it is disconnected again. Okay, any other question meanwhile? Okay, so this is like the simple example. I mean, of course, the whole point here is that there are many types of global symmetries you can think of, and then the consequences are non-trivial. So I'm not gonna give more examples because Miguel then will talk about generalized notions of symmetry. So these are like ordinary symmetries. But then, like in recent years, there has been a lot of activity on new notions of symmetries, higher force symmetries, non-invertible symmetries, and all these things should not be allowed in quantum gravity unless they are broken or gauged. So there are many interesting things that one can say. But I will let Miguel to discuss these more recent developments, okay? So let me, instead what I'm going to tell you is what is the evidence that we have for this conjecture, okay? Why we think that there are no global symmetries in quantum gravity? Why do we impose this? Okay, so basically there are different, I mean, I think this is the conjecture which is better understood. We have proofs in certain setups. I mean, we have arguments that make us believe that it's general. So let me go through them a bit. So first of all, we have some arguments based on black hole physics that give us, it's not a proof, but give us some intuition of what is the problem, okay, if we have a global symmetry. Then we have more refined arguments also based on black hole physics, but using all these recent developments of replica wormholes to describe the page curve, unitary evolution. And then we have some proofs, rigorous proofs. I mean, in string theory, like for example, it's known that in string perturbative theory, there are no global symmetries. And also in ADCFT more recently by Harlow and Oguri. In which one can show also that there are no global symmetries in the bulk. So let me start with this heuristic argument, okay? And then I will tell you a little bit about the holographic proof. Okay, so what is the intuition? Okay, so the idea is just consider some black hole, okay? This is just some sparsal black hole. This is the metric. And now, if this black hole, if there is a global symmetry, in my theory, I can construct black holes with different global charges. Okay, so I can construct black holes for all possible global charges. And the point is that all of them has the same metric. Okay, the global charge does not enter in the definition of the horizon. Okay, same metric, same horizon. So from very far away, they look the same. They look the same. There is no way to distinguish what is the global charge of the black hole. And this means that I have like infinitely many ways to construct the same black hole, which in the end translates into an infinite entropy. Okay, like intuitively, roughly speaking, like the entropy is associated to how many microstates I have, right? How many different ways I can construct the same thing. So if I have a global symmetry, it's like if I would have some black holes of infinite entropy. And one of the things that we know about black holes is that they have a finite entropy. They are thermodynamic objects, and they have an entropy given by the area of the black hole because they have some temperature, and this is finite. So it goes against this idea. Okay, so in the moment in which you have black holes in your theory, if you have something that cannot be distinguished from far away, like you can construct the black hole, and this information is lost outside of the black hole, that's a problem. Okay, that would violate some entropy. Okay. It's also possible to make this a little bit more concrete by thinking of remnants. So sometimes people say that a global symmetry gives rise to trouble with remnants because, I mean, you can construct all these black holes, let them evaporate. And since Hawking evaporation is blind to the global charge, you will not get rid of it. So that you end up in the end with an infinite number of nearly stable remnants, which are like Planck-sized objects that come from evaporating all these larger black holes. So you would expect that, yeah, like the number of states in your theory, you can sum over them with all possible global charges, and you sum over all possible masses, and this goes to infinity. Okay. So again, like in principle, you violate these entropy bounds because you have infinitely many states which are nearly degenerate, but they are still different. And we will see how, we'll see this week how, for example, if the symmetry is gates, this is solved, because then you can distinguish them from far away, because the gate charge, like the electric charge, changes the metric, changes the horizon, and therefore they are different and they don't count as the same state. Okay. Okay, good. So this is the heuristic argument. As I said, one can also, I mean, there are this series of papers that if you are interested in, you can take a look. The point is that the idea is that, yeah, all these recent developments about the page curve, what they show is that it's very important to consider topology changing processes, like all these replica wormholes. And whenever you have some process that changes the topology, this is going to break the global symmetry. Because a global symmetry, you will see later that is parameterized by some topological operator. It's something that is a topological invariant. But if topology itself can change, global symmetry is broken. So the global symmetry is only something that is well defined in quantum field theory when you have a fixed topology. In the moment in which you change topology, as happens in quantum gravity, is not a notion which is well defined anymore. Okay. So this is the intuition. In quantum gravity, topology fluctuates. It changes. And this breaks global symmetries because they are only well defined as topological operators in a fixed topology. Okay. So this is just some intuition. And then, yeah, like the proof that we have, let me also discuss this a little bit. Where is it? Okay. So the idea is that, yeah, what is the proof in perturbative string theory? So The point is that in perturbative string theory, if you have learned about string theory, you can have a worthy description and then the space-time description. And the point is that one can show that, let me just write it here, like any global symmetry in the worksheet it's going to be a gauged symmetry in the bulk, like in the space-time, okay? Target space. Because you can always construct a current. It's kind of a generalization of Nether's theorem. That's given a global symmetry in the worksheet, you construct a current and a gauge symmetry in space-time. Now, since actually it's very similar to the proof that we have from holography, because in holography it's going to be the same. What one proves is that a global symmetry in the boundary always corresponds to a gauge symmetry in the bulk. Since it's very similar, I'm just going to describe it in terms of holography, okay, and then it applies equally to perturbative string theory. By replacing, instead of talking about the CFT in the boundary, you talk about the CFT in the worksheet, but it's kind of the same, okay? Okay, so how do we understand this in holography? Well, so the point is, if I'm in a global symmetry, something physical, okay? So it's something that should not disappear under a duality, okay? Something that is invariant under duality frames, meaning that if I have a global symmetry in the bulk, I should also have a global symmetry in the boundary and vice versa. Okay, these are different dual descriptions, so a global symmetry cannot disappear. Now, in ADCFT, we know that any bulk operator, if you have some bulk operator, can be described, can be represented in the boundary as some operator acting on the boundary. And what Harlow and Oguri use to prove this is what is called entanglement wedge reconstructions. Okay, I cannot give you a full lecture about this, but basically it means that if you have like any operator let's take some region on the boundary, Ri, for example. If I have some operator in the boundary that lives in this region, it's represented some operator which lives in some region in the space that you can compute using Ryu-Takayanagi formula. And there is a one-to-one correspondence between them, okay? So any region in the boundary can only access some part of the bulk. And what's going on now? Well, the point is that if I have some global symmetry, which is splittable, okay? So this is an assumption that they impose, meaning that you have some operator in the boundary that you can split into different operators that act on different subregions. It's some notion of locality, okay? So that I can just divide this on different subregions, okay? Such that the full operator describing my global symmetry, I can split it into a product of operators acting on each of the subregions, okay? Then I can show that there is an inconsistency if the symmetry is global. Why? Well, because if I have some global symmetry in the bulk, it's a local operator that is localized. And I can make these subregions very small in such a way that they will not access this point in the bulk. So I don't get information about this local operator, meaning that this operator commutes with all my operators in the boundary, so that they don't have access. We don't have access to the global symmetry from the boundary. So there is no operator charge under the symmetry. There is no symmetry in the boundary. So this is a contradiction. Okay, the contradiction is that I have some global operator in the bulk, but there is no global operator in the boundary because I cannot access the information. So, and this is based on locality of the CFT. So what's the way to fix it? Well, the way to fix it is that if this global symmetry is gauged, it means that it will be attached to some Wilson line because it's associated to some gauged degree of freedom. And this Wilson line can propagate to the boundary. I have a new dynamical degree of freedom that propagates, and therefore the information will be carried to the boundary and will be trapped in one of these surfaces. So I cannot get rid of it. And then that's consistent. So what I saw is that any global symmetry in the boundary is actually associated to some gauged symmetry in the bulk because you can carry the information far away. Okay? Any question? Okay, so I hope this at least gives you some flavor of how the people prove the absence of global symmetries in ADS-CFT. Of course, I mean, it was a 5 minutes discussion, so if you want to know more details, you should look at the paper, but you can also ask me questions later on or now as you wish, okay? But okay, at least keep in mind this message that global symmetries in the boundary are necessarily gauged in the bulk. Okay, good. So let me come back then to to one of the questions that we had by one of the students, which is, can we quantify how much we have to break the symmetries? So, as I was saying, this statement is just telling me that the symmetries cannot be exact. Meaning that, okay, if they are not gauged, they must be broken. But it doesn't tell you what is the scale. It doesn't tell you how much. So when you want to use this for phenomenology, it seems it's not very useful. Okay, because the symmetry can be broken at very high energy scale. And the effects might be irrelevant in the IR. So it's a bit disappointing because we really want to give constraints for phenomenology. But this is not the end of the story. This is just the beginning. Okay. So what we are going to do in the rest of the week is to quantify how much we have to break these symmetries. And this is done by studying what are the most important conjectures in the Swampland program, which are the weak gravity, the weak gravity conjecture, and the distance conjecture. So they will give us information about how small the gauge couplings can be. So the weak gravity conjecture will tell us, that the gauge couplings that are gauging the symmetries cannot be too small. Because if they are too small, the cutoff of the EFT will go to 0. Because the cutoff is going to be proportional to the gauge coupling. Because there are new states that appear at a scale of order the gauge coupling or below. Okay. So it's quantifying like how much, in the sense that, okay, you can have a very small gauge coupling, but then the EFT is going to be valid only up to a very small energy scale. So you're going to be sensitive to new states, and this is going to change your EFT. Okay, so this is the new information that comes from quantum gravity, that small gauge couplings will come at a price. Okay, you have to add new states, you have a new cutoff. And this quantifies how small the gauge couplings can be. So it quantifies this notion of gauge. Okay. And then we'll see that the distance conjecture also like quantifies how much we approach to some points in which you would restore a global symmetry, regardless of whether it is gauged or not. Okay. So we'll see that this is going to constrain actually field ranges. Now it seems very disconnected from global symmetries, but the point is that when you, we'll see that when you change the vacuum expectation value of your scalar fields, you can prove different effective theories. And the points in which you have a global symmetry, when you have a global symmetry, they are pushed to infinite distance this field space. So the distance conjecture is going to tell you what is the physics near these infinite distance points in which you have approximate symmetries. And this is what we will understand during the rest of the week, okay? Now, even though I want to make a final comment that, okay, it's very important, I mean, in order to really give numerical implications, I mean, we need to quantify these things, we need to quantify how much we break them and gauge them, and this is what we will do with the weak gravity and the distance conjecture. But even then, in recent years, we have learned that just the statement that there are no global symmetries is actually more constraining than what we expect. So even without quantifying how much you have to break them, thanks to all this generalized notion of symmetries that have appeared in quantum theory, we can give non-trivial implications. Okay, so in the rest of the week, I will focus on the weak gravity and distance conjecture, but in Miguel lectures after me, he will focus on this. Okay, he will focus first on how even if the symmetries are exact, one can learn a lot from the absence of these new types of global charges. And there are actually many familiar phenomena in string theory that can be derived from the absence of global symmetries. Like, for example, the existence of branes, Chern-Simons terms, completeness of the charge spectrum, having compact gauge groups, having axions in your theory. Like, there are many things that just come just because you don't want to have an exact global symmetry. And for that, you have to understand better all these generalized higher force symmetries and so on. But it's something that you will learn just after me. And also how actually, if you consider this in supersymmetric setups, when you have supersymmetry, then this conjecture also becomes much more powerful. Because even without quantifying how much you break them, combining supersymmetry with no global symmetries becomes very powerful to classify the supersymmetric landscape. Okay, like try to say what are the possible theories that are consistent with quantum gravity and ask whether everything can be engineered in string theory or not. So you will learn about this supersymmetric stuff later. And in my case, I mean, in my lectures, what we will see is to try to quantify them to be able to connect with our universe, okay? Because once we break supersymmetry, then this constraint is, I mean, this becomes less constraining, and then we have to quantify how much we have to break or gauge the symmetries. So I will focus more on this non-supersymmetric universe in a sense, in which we need to quantify how much we have to break and gauge them, okay? So as I said, like tomorrow, we will learn about my favorite conjecture, which are the weak gravity and the distance conjecture. And I will finish here today. Are there more questions?
Thank you very much for excellent talk. Are there questions? Yes, there is one question. Please go ahead.
I have rather naive questions. So if you have a duality between weak and strong coupling, can you say maybe there is some bound on how strong the gauge coupling can get as well? And yes, and the other question was about that if we send M Planck to infinity, we assume all the Swampland constraints are not there anymore. So I was wondering if there may be some discontinuity that forbids this.
Okay, yes, good questions. So for the strong gauge coupling, the thing is, yeah, we'll see the weak gravity conjecture has something to say. You can always think of dualizing in a sense, like roughly speaking, right? Like if the electric gauge coupling is strong, is very large, typically it's like a magnetic version, which has a gauge coupling which is very small. So you can always go to a different frame in which what you call magnetic becomes electric. And then in that frame, it's like having a small gauge coupling. And then again, you are gonna get new states becoming light. And this is something that the weak gravity conjecture will quantify. But yeah, whenever you take some extreme limit, in a sense, in some parameter, probably, I mean, most likely, this is going to be associated to some symmetry being restored, and we'll see that there are constraints coming from quantum gravity in that case. Now, regarding the second question, yeah, all these Swampland constraints disappear when the Planck mass goes to infinity, because it's very important that gravity is dynamical. And then you can ask, okay, what happens in the limit, right? Like there is some, I mean, like, is there something going wrong when I take the limit? And this is precisely a very similar question to, well, maybe let me write it here, to what happens when you have an approximate symmetry. So the point is that let's think of gauging. So if its gauge is fine, but now we say, I mean, we'll see that with the weak gravity conjecture, the point is that it quantifies that the gauge couplings cannot be too small, okay? But too small in terms of the Planck mass. So what happens here? Well, what happens is that here I was taking a frame in which the Planck mass is finite, it remains constant. And I was telling you that if this gauge coupling goes to 0, then the cutoff also goes to 0. So that there is a continuous, I mean, as you approach the limit, as you approach the limit, okay, anyway, listen. So as you approach the limit in which a symmetry will be restored, the EFT is going to break down in a continuous way, because the EFT cutoff is going to 0, and it's 0 in the limit in which you restore the symmetry. Now, instead of keeping the Planck mass fixed, you can think that what you are doing is to send the Planck mass to infinity, and it's kind of the same. Like, it depends what is the frame that you take. So things happen in a continuous way. It's not something abrupt. What happens is that as you decouple these things or you take these limits, the cutoff will be sensitive and will change in a continuous way. So that if you keep the Planck mass finite, the cutoff goes to 0. If you allow the Planck mass going to infinity, the cutoff can still be very large, and there is no problem, but in a continuous way.
Thank you. Thank you.
Any other question? So, wow, you don't see any. Thank you very much, Irene, for a great talk.
Okay, thank you all for listening. See you tomorrow.
We'll see you tomorrow, yes. And we come back in half an hour with Miguel's talk.